blackness between galaxies. You'd think it's just
Yeah.
nothing, right? A total void, no stars, no planets, almost zero gas. But what if I said that very nothingness isn't just empty, but it's actually curving? I mean, how can empty space bend? And maybe even weirder, what is it that's doing the bending? It kind of messes with your basic idea of reality, doesn't it?
It absolutely does. And you've really hit on one of the most profound questions in, well, all of modern physics. The good news, though, is it's not really a paradox. It's more like a gateway, actually, a gateway to understanding two huge shifts in how we saw the universe in the 20th century, general relativity and quantum field theory.
Okay.
Now, what we think of as empty space, it's just far from being a passive void. It's actually this dynamic physical thing we call spacetime. And its properties are fundamentally geometric. And what's more, what we call empty, well, on the quantum level, it's the lowest energy state of all these fundamental quantum fields. And it's absolutely brimming with latent energy.
Right, so not really empty at all then. Okay, so our mission for this deep dive then, let's lay it out. We're going to try and deconstruct this incredible question. We'll contrast those older classical ideas of space with modern physics. We'll really establish space-time as this dynamic, geometric thing, show how it gets shaped by matter and energy, and then tackle that two-part answer you mentioned. How does curvature exist in a vacuum? How does it travel through nothing, like gravitational waves? And how is the vacuum itself this energetic medium that can actually create curvature?
Exactly. And we need to ground all these, pretty abstract ideas with the solid evidence we have from observations.
Definitely. So to really get how empty space curves, we first need to ditch that intuitive idea that space is just this passive backdrop. The history here, from Newton to Einstein, it's really the story of space changing roles, isn't it? From background stage to active player. And the thing that curves, the actual entity, is this physical construct, space-time.
Precisely. If you go back to the Newtonian view, Isaac Newton's picture, space was thought of as this fixed, infinite, unchanging 3D grid. Like a static stage, totally absolute. Everything happened on it, but it wasn't affected by it.
And time was separate, too.
Completely separate.
Yeah.
Just this universal clock ticking away at the same rate for everybody, everywhere, independent. And gravity in that picture was just a force, an instantaneous force acting between masses across that space. The inverse square law.
And it worked incredibly well. Explained planets moving, even predicted Neptune. So what were the problems? What pushed physics beyond that?
Oh, for centuries it was the description. And it's still amazingly accurate for, most things we do day to day, sending rockets to the moon, building bridges. But little cracks started showing. It couldn't quite nail the orbit of Mercury, for instance. There was this tiny anomaly in its precession.
There's precession, right.
But maybe more fundamentally, the core issue was just that. Space and time were separate, absolute, and inert. Just a stage. They didn't do anything.
Okay, so that incredibly successful Newtonian picture started to fray at the edges. What came next? This must be Einstein.
Einstein, yes. Special relativity, 1905. It really grew out of this conflict between Newton's mechanics and Maxwell's equations for electricity and magnetism, especially about light.
Light's behavior was weird.
Exactly. And the central idea, the truly radical postulate, was that the speed of light in a vacuum is constant for all observers.
Regardless of how fast they're moving.
Right, and that simple-sounding principle has this huge consequence. Measurements of distance and even duration, time itself, become relative. They actually depend on who's measuring, on their motion.
Whoa, so my meter stick might not be the same length as yours if we're moving differently, and my clock ticks differently.
Essentially, yes. And the really profound consequence of that was realizing space and time aren't independent anymore. They're absolutely interwoven. They form a single, four-dimensional continuum. Space-time.
Space-time, okay.
And that just shattered the idea of absolute simultaneity. Events that look simultaneous to you might not look simultaneous to me if we're moving relative to each other.
Mind-bending stuff already.
Yeah.
But this space-time, it was still rigid. Flat.
Still rigid, yes. At this stage, it was flat. Think of Minkowski space-time. A fixed, non-interactive stage, but now four-dimensional. It didn't bend or curve yet. That was the next step.
And that next step was the really big one, general relativity, 1915. This is where space-time finally becomes alive, dynamic. Einstein basically said the geometry of space-time isn't fixed, right? It actually changes. It responds to matter and energy.
Precisely. And this is where gravity gets redefined. It's not a force pulling things across space anymore. Gravity is the curvature of space-time. Objects, planets, light beams, they're all just following the straightest possible paths geodesics through this curved landscape.
Okay, but what is this space-time fabric then? If it's not just emptiness, what is it?
That's the million-dollar question, isn't it? The answer, mathematically at least, lies in something called the metric tensor. You can think of it as like a set of rules, a rule book embedded at every single point in spacetime that tells you how to measure tiny distances and durations between nearby events in all 4 dimensions.
So it defines the geometry locally.
Exactly. In flat spacetime, like in special relativity, those rules are the same everywhere. The metric is constant. But in general relativity, the components of this metric tensor vary from point to point, and those variations tell you precisely how the local geometry deviates from being flat. So the thing that's curving is spacetime itself, this 4-dimensional manifold. And its geometric properties are encoded by this metric tensor field, and that field is just as real as the electromagnetic field. Its curvature is gravity.
And objects follow geodesics, like an airplane flying the straightest path on a curved Earth, which is a great circle.
That's a great analogy, actually. The plane feels like it's going straight, but its path is dictated by the curvature of the Earth. Planets are doing the same, taking the most direct route through spacetime's curves. They're essentially in free fall along those paths.
This just completely rewrites the rule book. It's such a profound shift from that static 3D stage and absolute time of Newton,
Right.
where gravity is a force acting instantly, mass is the only source, to this dynamic 4D space-time where time is relative, gravity is curvature, and the source is much broader.
Much broader. It's not just mass. It's all forms of energy, momentum, even pressure. And the influence, the gravitational effect, propagates the speed of light, not instantly.
And light itself gets bent, which Newton didn't predict.
Right. Gravitational lensing. That's a direct consequence of light following geodesics through curved spacetime. It's a fundamental difference.
Okay, so we've got spacetime as this dynamic geometric thing. Now, what actually tells it how to curve? This is where the equations come in.
This is the heart of it, yes. The Einstein field equations. There's that famous aphorism by the physicist John Wheeler that sums it up beautifully.
Spacetime tells matter how to move. Matter tells spacetime how to curve.
Exactly. It's this incredible dialogue. Let's focus on the second part first. Matter tells spacetime how to curve. This is represented mathematically by something called the stress-energy tensor, and it's way more than just mass.
You mentioned energy, momentum, pressure.
All of it. It's like the complete source recipe for gravity. It includes the energy density locked up in mass, that's your EMC/ASN, but also energy in fields like electromagnetic fields or even just the kinetic energy of heat. It includes momentum density, the flow of energy, like the momentum carried by light, and it includes pressure, like inside a star, and even things called shear stresses, which are forces that cause distortion.
So basically, any form of energy or momentum or pressure warps spacetime, not just lumps of matter.
That's the radical departure from Newton. It's everything. Which immediately makes you wonder, what about a perfect vacuum? If there's no matter or energy, the stress-energy tensor is 0. How can spacetime still be curved then?
Right. Good question. But before we get there, what about the other side of Wheeler's phrase, spacetime tells matter how to move? How is the curvature itself described?
That's represented by the other side of the equation, the Einstein tensor. This is built purely from the geometry itself. It's constructed entirely from the metric tensor and how it changes from point to point, its derivatives. It's a direct, sophisticated measure of spacetime curvature.
So it quantifies the bendiness.
Precisely. For instance, one part of it, the Ricci tensor, effectively measures how the volume of a tiny ball of dust particles changes as it floats freely through spacetime. If space is positively curved, like on a sphere, that volume shrinks faster than it would in flat space. Geodesics converge. It gives you a number. This is how curved it is right here.
Okay, so you put these two sides together, the geometry side, Einstein tensor, and the stuff side, stress-energy tensor.
And you get the master equation. Einstein tensor equals some constants times the stress-energy tensor, gen Hkin. It's this elegant tensor equation establishing a direct local link. This much stress energy here causes this much curvature here.
Simple looking, but incredibly powerful.
And what's really crucial and different from many other theories like electromagnetism is that this equation is nonlinear.
Nonlinear, meaning?
Meaning the gravitational field interacts with itself. Think about it. The gravitational field carries energy, but we just said all energy source is gravity.
Ah, so the energy in the gravitational field can create more gravitational field.
Exactly. It acts as its own source. This self-interaction is absolutely key. It's how gravity's influence can propagate through empty space, far from the original matter that created it. It's this continuous feedback loop. Stress energy shapes geometry. Geometry dictates motion. Motion involves energy, which feeds back into shaping geometry.
Okay, That self-interaction idea seems vital for the vacuum question, so let's tackle it head-on. How can space-time be curved where there are no local sources? In a vacuum, what's the first part of the answer?
The first part comes straight from general relativity itself. Curvature is a property of the gravitational field, and that field can persist and travel, even where the original source isn't present.
Like ripples spreading out.
Sort of. Think about the space around our sun. It's practically a vacuum out here where Earth is. The stress-energy tensor, T, is essentially zero. Now, if you plug T into the full Einstein equations, they simplify to GIN, which actually means the Ricci curvature part must be zero.
Okay, Ricci curvature is zero in a vacuum. That sounds like it should mean flat space.
It sounds like it, but it doesn't. Because space around the sun is definitely not flat. That curvature is what keeps Earth orbiting. The sun's influence, its curvature extends outwards. It gets weaker, sure, but it's still there. Earth responds to the local curvature right here.
So the curvature isn't generated here, but it's present here, inherited from the sun.
Precisely. A famous example is the Schwarzschild solution. It describes the space-time outside a non-rotating star or black hole. It's a vacuum solution, Ricci flat, but it's definitely curved.
Okay, how does that work mathematically? If Ricci curvature is zero, what kind of curvature is left?
This is where we need to break down the full curvature description, the Riemann tensor, into its components. As you hinted, there's Ricci curvature, but there's also something else called Weil curvature.
Ricci and Weil, what's the difference?
The Ricci curvature is the part directly tied to local matter and energy. If T isn't zero, Rien generally isn't zero. In a vacuum where T is zero, Ricci curvature must be zero. Physically, it relates to volume changes, how matter squishes or stretches the volume of space-time locally.
Got it. So Ricci, local stuff. What about Weil?
Weil curvature is different. It's not directly tied to the local stress energy. It can be non-zero, even in a perfect vacuum where Ricci is zero. Physically, it describes things like tidal forces, the stretching and squeezing, and shape distortions. Crucially, it represents the propagating sort of wave-like aspects of the gravitational field itself.
Ah, so that's the loophole. Empty space can be curved because even if the Ricci part is zero, no local sources, the Weil part can still be non-zero.
Exactly. That non-zero Weil curvature is the imprint or the message from a distant source, like the sun's gravity reaching us. Its specific shape is determined by those faraway sources, the boundary conditions.
And the most dramatic example of pure propagating Weil curvature must be
Gravitational waves. Absolutely. Predicted by Einstein way back in 1916, finally detected directly by LIGO in 2015, a monumental achievement.
Tell us about those waves again. They're literally ripples in space-time.
They are. Generated by incredibly violent events, like two black holes merging. They are pure Weil curvature, completely detached from their source, traveling across the universe at the speed of light. They carry energy and information through the vacuum. When a wave passes through, say, the LIGO detector, it stretches space-time in one direction and squeezes it in the perpendicular direction back and forth.
And LIGO measures that tiny stretch and squeeze.
Incredibly tiny, smaller than 1/10,000th the diameter of a proton over its 4-kilometer arms. But they measure it.
That detection is just undeniable proof, isn't it? Space-time is real, it's physical, it can be disturbed, and those disturbances travel through empty space.
Irrefutable proof. The thing curving is space-time itself, and its ripples travel through the vacuum.
And that connects back to the nonlinearity you mentioned, the field's own energy allowing it to propagate.
Yes. When a source creates curvature, that curvature contains energy. That energy sources more curvature, which contains energy, and so on. This allows the influence to essentially break free and travel as a self-sustaining wave, pure geometry rippling outwards.
Okay, so that's one major piece. Curvature from distant sources persists and propagates as Weil curvature, even as gravitational waves. What's the second part of the answer? You mentioned quantum field theory.
Right. This is equally profound, and it changes what we even mean by vacuum. Classically, vacuum is just nothing, empty space. But in quantum field theory, QFT, the universe isn't built from tiny billiard balls, but from fundamental fields permeating everything. Electron field, photon field, Higgs field, etc.
And particles are just excitations in these fields, like waves on an ocean.
That's a good way to think of it. Particles are localized vibrations or excitations. So from this QFT perspective, the vacuum is defined as the lowest possible energy state of all these fields combined, the ground state of reality.
So even if you remove all particles, all radiation, cool it to absolute zero, The fields are still there.
The fields are still there in their lowest energy configuration.
And this is where it gets really weird, right?
Yeah.
Because quantum mechanics doesn't like things sitting still.
Exactly. Enter the Heisenberg uncertainty principle. Specifically, the relation between uncertainty in energy and uncertainty in time. It basically says you can't have a quantum field be perfectly zero or perfectly static. There are always inherent, unavoidable quantum jitters, vacuum fluctuations.
So the vacuum isn't quiet and empty. It's buzzing, seething.
Seething is a good word. It's incredibly dynamic.
Right.
We often picture this as pairs of virtual particles and antiparticles constantly popping into existence, borrowing a tiny bit of energy from the vacuum, existing for an impossibly short time, and then annihilating each other, paying back the energy.
Virtual particles.
Yeah.
Do they have real effects?
Yeah.
Or are they just a mathematical trick?
Oh, they have real measurable consequences. That's the key.
Yeah.
The Casimir effect is a classic example. Predicts an attractive force between two neutral parallel metal plates placed very close together in a vacuum. Because the space between the plates restricts which virtual particle wavelengths can fit compared to the outside. Fewer modes inside means lower energy density between the plates, effectively pushing them together. And it's been measured.
Wow. Okay, what else?
The Lamb shift. A tiny shift in the energy levels of the hydrogen atom that wasn't predicted by older quantum theory. It's perfectly explained by the electron interacting with these vacuum fluctuations. Even spontaneous emission, an excited atom spitting out a photon, is fundamentally triggered by the atom interacting with vacuum fluctuations. Lasers wouldn't work without it.
So this empty space is actually a very active place, physically influencing things.
Powerfully confirmed, the vacuum is not a void, it's a physically active structure.
And this activity, these fluctuations, they imply energy, right? Even in the lowest state.
Yes, that's the concept of zero-point energy, or more broadly, vacuum energy. It's the minimum possible energy that remains even when you've removed everything else. It's an intrinsic, non-removable property of the vacuum itself.
Okay, bring it back to gravity. General relativity says all energy curves space-time.
Therefore, the intrinsic energy of the vacuum itself must have a gravitational effect. It must curve space-time.
So space is never truly empty in a way that stops it from sourcing curvature, because the vacuum itself has this inherent energy density.
Precisely. It acts as a ubiquitous source of a sort of baseline curvature throughout the entire universe.
And this isn't just some tiny theoretical effect. This quantum vacuum energy has massive consequences for cosmology.
Huge consequences. It ties directly into the story of the cosmological constant, usually written as lambda. Einstein first put it into his equations to force the universe to be static, which everyone thought it was back then. When Hubble found the universe was expanding, Einstein famously called lambda his biggest blunder.
But it came back.
It came back with a vengeance. Because mathematically, the cosmological constant term behaves exactly like a constant energy density spread uniformly through space, exactly like vacuum energy. You can move the lambda term over to the other side of the Einstein equation and interpret it as the stress energy of the vacuum itself.
And what does this vacuum energy do gravitationally?
A positive vacuum energy density corresponds to having negative pressure. And negative pressure in general relativity exerts a repulsive gravitational force. It pushes spacetime apart. It provides a baseline anti-gravity.
Which leads us straight to
Dark energy. The discovery in 1998 from observing distant supernovae that the expansion of the universe isn't slowing down due to gravity, as everyone expected.
it's accelerating, speeding up, Nobel Prize-winning stuff.
Absolutely. And this mysterious dark energy driving the acceleration makes up about 68% of the total mass energy content of the universe. The simplest and currently most favored explanation is that dark energy is the energy of vacuum, represented by a small positive cosmological constant.
So in the early universe, matter's gravity dominated, pulling things together or slowing expansion.
Right. But as the universe expanded, matter got diluted. The vacuum energy density, however, stays constant. It doesn't dilute.
So eventually its repulsive effect became dominant over matter's attraction.
And started accelerating the expansion, which is what we see today.
Incredible. But then there's a problem here, isn't there? A big problem. The cosmological constant problem.
Oh, it's arguably the biggest problem in fundamental physics. The discrepancy is just staggering. When theoretical physicists try to calculate the vacuum energy density using quantum field theory, basically adding up the zero-point energies of all known quantum fields up to some cutoff energy scale.
They get a number.
They get an enormous number, truly mind-bogglingly huge. But the value we actually observe from cosmology, the value needed for dark energy to explain the acceleration,
is tiny.
Incredibly tiny in comparison. The theoretical prediction is larger than the observed value by a factor of, well, estimates vary, but it's somewhere between 10 urines and 10 15s.
10, followed by 50 to 120 zeros. That's insane.
It's been called the worst theoretical prediction in the history of physics. It highlights this massive chasm, this deep disconnect between general relativity, our theory of gravity in the large scale, and quantum field theory, our theory of particles in a small scale.
So something's wrong. Or missing.
Something fundamental is missing. It strongly suggests there must be some unknown physical principle, maybe a new symmetry, that cancels out almost all of that enormous theoretical vacuum energy, leaving just the tiny sliver we observe. Finding that cancellation mechanism is a holy grail for theories trying to unify gravity and quantum mechanics theories of quantum gravity.
So the vacuum does source curvature, but the huge mystery is why it sources so little. Why doesn't this enormous predicted energy just rip the universe apart instantly?
That is precisely the mystery. Why is the vacuum so gravitationally gentle? We don't know.
Wow. Okay, through all this theory, it's crucial to remember, as you said, this isn't just math. General relativity, curved spacetime, it's been tested rigorously for over a century.
Absolutely. The observational evidence is overwhelming. Take gravitational lensing. GR predicts light bends near mass. Einstein calculated 1.75 arcseconds for starlight grazing the sun, double the old Newtonian idea.
Eddington confirmed it during the 1919 eclipse, right? Made Einstein famous overnight.
Exactly. And today we see it everywhere. Massive galaxies and galaxy clusters act like giant lenses in space. They bend and magnify light from objects behind them, creating these beautiful distorted arcs, sometimes multiple images of the same quasar, like the Einstein cross, or even complete circles called Einstein rings.
That's just direct visual proof that space-time is curved, and light follows those curves.
Undeniable. And then, of course, the direct detection of gravitational waves by LIGO and Virgo.
We talked about how LIGO works, detecting those tiny stretches and squeezes.
Hearing the chirp of two black holes merging billions of light years away, it's tangible proof that spacetime is a physical medium, that ripples of pure curvature travel through the vacuum, that spacetime is the thing that curves.
And there are other foundational tests, too.
Loads of them. Gravitational time dilation clocks ticking slower and stronger gravity, confirmed experimentally back in 1959, and it's utterly essential for GPS to work.
Right. The satellite's clocks run faster up there. Without corrections, GPS would send you miles off course within hours.
Kilometers per day, easily. It's a real-world GR effect we rely on constantly. And then there's the perihelion precession of Mercury. That small discrepancy Newton couldn't explain.
GR nailed it perfectly.
Nailed it. It was one of the first major triumphs of the theory. So yes, all these tests together build an incredibly strong case. The geometric view of gravity is correct. Space-time curvature is real and verified.
Okay, to really hammer this home, let's talk about a common analogy people use: the bowling ball on the rubber sheet. It's so popular for visualizing curved space.
It is popular, and it does capture one aspect, visually mass, causing a depression. But it's deeply flawed if you take it too literally, especially for understanding general relativity.
What's the main flaw?
The biggest one is that it uses gravity to explain gravity. The bowling ball makes a dent because Earth's gravity pulls it down onto the sheet. The marbles roll downhill into the dent because Earth's gravity pulls them.
Ah, so it's really a model of a Newtonian potential, well, not Einstein's curved spacetime.
Exactly. It's showing a force acting in a fixed space. In GR, remember, there's no force of gravity pulling the planet. The planet is just following the straightest path, geodesic, through space-time that's already curved by the sun. It's in free fall. The marble on the sheet is being acted upon by forces.
And it visually implies you need an extra dimension for space-time to curve into, which isn't required either.
That's another misleading aspect. Yes, curvature is an intrinsic property.
But you said the most critical omission is?
The curvature of time. The rubber sheet only shows curved space in 2D, but GR is about curved space-time.
How does that play out?
Well, think. An object just sitting still on the rubber sheet just sits there. But if you hold an apple above the Earth and let go, it falls. Why does something stationary in space start moving? The rubber sheet offers zero explanation.
So what is GR's explanation for the falling apple?
It's because even when the apple is stationary in space, it's still moving through time. And in a gravitational field, space-time is curved such that the straightest path forward in time for an object at rest in space actually points downwards spatially.
Because time flows differently at different heights.
Precisely. That's gravitational time dilation again. Time runs infinitesimally faster higher up. An object in free fall, like the apple, is essentially following the path through space-time that maximizes the amount of time passing on its own wristwatch, its proper time. It's aging as much as possible.
So everyday gravity, like dropping an apple, is less about space being bent and more about the rate of time flow changing with location.
That's the crucial insight for weak gravity like Earth's, and the rubber sheet completely misses it. Understanding why the analogy fails actually forces you to grasp the deeper, more subtle, and frankly more beautiful reality of general relativity.
This has been quite the journey then, this deep dive into how empty space can curve and what's doing the curving. It really forces you to abandon those classical intuitive ideas. We have to rethink space, rethink emptiness.
And the definitive answer synthesizing everything is that the thing curving is space-time itself. It's not a void. It's this dynamic, physical, 4D manifold. Its geometry is encoded by the metric tensor field everywhere. That geometry is the fabric of reality, dictating how everything moves.
And the answer to how it curves in a vacuum is twofold.
Twofold, exactly, coming from our two pillars of modern physics. First, general relativity tells us curvature persists and propagates in vacuum via the gravitational field itself. That's the wild curvature carrying the message from distant matter or breaking free entirely as gravitational waves.
That's right, the field as its own messenger.
Second, quantum field theory tells us the vacuum isn't empty. It's the ground state of quantum fields, buzzing with fluctuations and possessing intrinsic vacuum energy.
And that vacuum energy itself acts as a source of baseline curvature,
Yeah,
dark energy.
exactly. It's a ubiquitous source woven into the fabric of space itself.
So space-time is truly active, gets curved by stuff, its curvature can travel on its own, and it even curves itself just by existing as a quantum vacuum.
It's an active participant in the cosmic drama, but the synthesis leaves us staring right at that colossal mystery, the cosmological constant problem.
That 10 to the many zeros discrepancy between the predicted vacuum energy and the observed value.
It shows just how profound the disconnect still is between gravity and quantum mechanics. Our understanding is fundamentally incomplete. The final answer seems to lie hidden in a future theory of quantum gravity. And so the truly provocative thought to leave you with is this. Why is the vacuum so incredibly gentle? Given the immense energy QFT suggests it should have, why doesn't it violently curve space-time and tear the universe apart in an instant? That remains perhaps the greatest unsolved puzzle in all of fundamental science.